Welcome to the NPTEL course on Refrigeration and Air Conditioning. I am Ram Gopal from the Department of Mechanical Engineering. I would like to begin this course with a brief history of refrigeration, and the specific objectives of this particular lesson are to define refrigeration and air conditioning, then introduce the historical aspects of natural refrigeration methods and artificial refrigeration methods. At the end of the lesson, you should be able to identify various natural and artificial methods of refrigeration, list salient points of various refrigeration techniques, and name important landmarks in the history of refrigeration. Let us look at the definition of refrigeration. Refrigeration is defined as the process of cooling of bodies or fluids to temperatures lower than those available in the surroundings at a particular time and place. So you can notice that in refrigeration, cooling is involved, but refrigeration is not exactly same as cooling. So what is the difference between refrigeration and cooling? Cooling can be a spontaneous process, and the final temperature need not be same as the need not be lower than the surrounding temperature, whereas in refrigeration not a spontaneous process, and the end final temperature should always be lower than the surroundings. So this is the main difference between normal cooling process and a refrigeration process. For example, cooling of a hot cup of coffee. If you take a cup of coffee and you leave it on the table, it cools down. However, its final temperature cannot be lower than the surrounding temperature. Okay, so this is an example of a cooling process, but it's not an example of refrigeration process because the final temperature is not lower than the surrounding temperature. Let us look at the second example, cooling of a glass of water by adding ice. When you add sufficient amount of ice, the final temperature of the water will be lower than the surroundings. So this is an example of refrigeration. Okay. Now let us define air conditioning. Air conditioning refers to the treatment of air so as to simultaneously control its temperature, humid moisture content, quality and circulation. So why do we want to do this? We want to do this because this is required for occupants in thermal comfort, and it's required for a process or products in the space. Now what are the applications of refrigeration and air conditioning? Refrigeration is mainly required in various food processing and food preservation operations, and refrigeration is required in almost all chemical and process industries. It is also required for comfort and industrial air conditioning, and there are also several other applications of air conditioning and refrigeration, such as in medicine, construction, sports, etc. Now the history of refrigeration can be divided into two phases. First one is the age of natural refrigeration, beginning with the prehistoric times to the end of 19th century or to the beginning of 19th century, and the age of artificial refrigeration from 19th century onwards. Now let us look at some of the natural refrigeration methods. Why do we call it as natural refrigeration methods? Because we rely on nature for providing refrigeration. The most important of these is the use of natural ice. Natural ice can be obtained from colder regions, and it can be transported to regions where it is not available. For example, ice is available in polar regions, so you can cut blocks of ice from the polar region, and they used to be transported to other areas. This used to be actually a very flourishing business in olden times. Of course, the ice used to come all the way from America to even to India, in countries like India. Then the second method is harvest the ice in winter and store it for use in summer. There are several countries where the winters are very harsh, so you can actually make ice. Lakes and rivers freeze in winter, so you cut the ice blocks and store them in ice houses and use them in summer. This is the second popular method. And the third method is production of ice using nocturnal cooling. This is the method which has been used for centuries in countries like India and Middle East. So now let us look at the principle of nocturnal cooling. So in nocturnal cooling, you leave a shallow pool of water in night sky. Okay, and for the water to become ice, its temperature has to be brought down from 0 degree centigrade, from the initial temperature to 0 degree centigrade, and at 0 degree centigrade it has to lose its latent heat of fusion so that ice can be formed from the liquid water. So for this to happen, you have to have a heat sink whose temperature is much lower than 0 degree centigrade, and your surrounding air, for example surrounding air and and the earth cannot act as heat sinks, because their temperature in tropical countries will always be greater than 0 degree centigrade. However, if the sky is very clear, then the pool of water can lose heat by radiation to the stratosphere, and the stratosphere is typically at a temperature of about minus 55 degrees centigrade. So it is possible for the temperature of water to be lower than the 0 degree centigrade. So this is the process, or this is the principle behind nocturnal cooling. However, it's not nocturnal cooling has its own limitations. For example, what are the limitations of nocturnal cooling? It's not possible to make ice when the sky is not clear. For example, when the sky is cloudy, then the reflection radiation gets reflected back, and ice formation will become difficult. And for ice to be made, you have to have good insulation around the shallow pool of water. So insulation is required. And the third problem is that you cannot make thick slabs of ice. It has to be a shallow pool of water. So these are the major disadvantages of nocturnal cooling, ice formation by nocturnal cooling. So now let us look at another natural refrigeration method, that is the use of evaporative cooling. So whenever water evaporates into surrounding air, it produces a cooling effect, because evaporation is an endothermic process. So this is the principle behind the cooling of water stored in earthen vessels, and this is also the principle behind the cooling of human bodies on a hot day. That is how we lose the heat on a hot day. However, this has its own limitations. The evaporative cooling is very effective when the surrounding air is dry. If the surrounding air is very humid, then evaporation cannot be effective. So that's the reason evaporative cooling works very well in dry areas such as deserts, but it doesn't work well in coastal regions. And the third natural method is cooling by salt solutions. So we know that when we dissolve certain salts and certain materials in water, the water temperature drops. This is because the mixing of these salts with water is an endothermic process. So it takes heat from the surrounding water, and the resulting solution becomes cold. And by changing the salts, you can get different temperatures. However, this method again has its own practical limitations, because the cooling that is produced is generally limited. And also the recovery of salt is a difficult process. So let us summarize the limitations of natural methods. The first limitation is that they depend on local conditions, and they are uncertain due to dependence on weather, and it's difficult to produce large amount of refrigeration using any of these natural methods, and they were not really available to everybody. So these are the main problems with natural methods. Hence people have tried to produce refrigeration artificially. So let us look at artificial refrigeration methods. The early attempt, as per the scientific records, the credit for producing artificial ice goes to Professor William Cullen of Scotland. What he has done is he has brought ethyl ether in thermal contact with water under an evacuated glass bell jar. So the water formed from ice formed from liquid water as ether boiled. This involved two thermodynamic principles. First principle is that when you reduce the pressure acting on a liquid, its boiling point also reduces. For example, ethyl ether has a normal boiling point of 34 degrees centigrade. That means at 1 atmospheric pressure, it boils at a temperature of 34 degrees centigrade. However, if you reduce the pressure, then it will boil at lower temperatures. And the typical relationship okay. So another principle is that boiling is an endothermic process. That means heat has got to be supplied from the surroundings so that ice can form. Okay, so these are the two main principles involved behind Professor Cullen's experiment. That is summarized here. Okay, so absorption of large quantity of heat when a liquid boils at low temperature under the action of vacuum. You can see that this process is not a spontaneous process, because some external effort is required to maintain the vacuum. That means you have to have some vacuum pump, and which requires some mechanical energy input, so that continuous vacuum can be maintained in the bell jar. So this is not a spontaneous process, and this process is not also very useful in practice, because once all the ether evaporates, then there won't be any refrigeration. So if you want to make it practical, what we have to do is we have to recycle the ether. That means what we have to do is we have to condense the vapor back into liquid and send it back. Okay, so that means this calls for a cyclic, some kind of a cyclic process. Okay, so based on this, several refrigeration cycles have been devised. So let us look at one of the most important cycles, that is what is known as Vapour Compression Refrigeration System. Here refrigeration is obtained again when a liquid boils under low pressures or under pressures in such a way that its boiling point is lower than the surrounding, so you get refrigeration effect. So this is what is known as Vapour Compression Refrigeration System, and as we shall see later, we use a compressor here for producing the required suction conditions and for enabling condensation. The concept of Vapour Compression Refrigeration Systems was first given by Oliver Evans, an American engineer, in 1805, but we really do not know whether he has built a system based on this principle or not. The credit for building an actual Vapour Compression Refrigeration System goes to Jacob Perkins. In 1835, he has built a complete Vapour Compression Refrigeration System using ethyl ether as the working fluid. Even though this system worked very well, it was not a commercial success. One of the problems with the early system is that ethyl ether is used as a refrigerant. Ethyl ether, as I already mentioned, has a boiling point of about 34 degrees centigrade. So if you want refrigeration, you have to lower the pressure above that. That means the evaporator where the cooling takes place should operate under vacuum. Now when the evaporator operates under vacuum, there is a possibility of air entering into the system. Once air enters into the system, it can form an explosive mixer with ether. So this is one of the main problems with ether. Second problem with ether is that ether is also toxic. So people have tried to develop new refrigerants or new working fluids and systems based on new working fluids. Before discussing those things, let me show the Jacob Perkins machine. You can see that it has 4 basic components. This is the evaporator, so evaporator is shown here, compressor, condenser and an expansion valve. So these are the 4 basic components of any Vapour compression refrigerant system. The evaporator is submerged in a pool of water which needs to be cooled, and the condenser is submerged in a pool of water where heat rejection has to take place. Now let us look at the operation. Ether which is at a low pressure boils in the evaporator here. Since boiling is endothermic, it takes heat from the surrounding water and surrounding water gets cooled. Now the compressor takes out whatever vapor is generated and it compresses the refrigerant vapor to a high pressure, and when this high pressure refrigerant vapor flows through the condenser, it rejects heat to the surrounding water and it becomes a high pressure liquid. At this point you have a high pressure liquid. This high pressure liquid, to complete the cycle, flows through an expansion valve, and during this process its pressure and temperature drops and the cycle repeats. So this is the basic principle of any Vapour compression refrigerant cycle, and this is a schematic of Jacob Perkins system. You can see that in Jacob Perkins system a hand operated compressor is used. This is similar to our boring pump. And this photograph shows the working model of Perkins machine made by John Hague in London. Now let us look at other pioneers. Alexander Twining in 1950 has suggested Vapour compression systems that use apart from ether, ammonia and carbon dioxide. Then James Harrison actually has obtained a patent in 1856 for constructing Vapour compression refrigerant systems using ether, alcohols or ammonia. In fact, James Harrison's machines were very successful, and he is a man who has really commercialized the Vapour compression refrigerant systems. Then Charles Tellier of France patented a dimethyl ether based system in 1864. Dimethyl ether has a lower boiling point compared to ethyl ether, but the major problem with this is that it is also toxic. Now let us look at other landmark events. In 1874, Raoul Pictet has designed the first sulfur dioxide based system in Geneva. This system was very successful and it was used for almost 60 years in domestic refrigerators. One advantage of sulfur dioxide is that it acts as a auto lubricant. That means you really don't require another lubricating oil in the system, and also it has relatively low latent heat of vaporization, so it is very suitable for small systems such as domestic refrigerators. However, one problem with sulfur dioxide is that when it mixes with water, it forms sulfuric acid, and when sulfuric acid is formed, it's corrosive and it damages the parts. Because of this reason, sulfur dioxide was used for almost 60 years, and in 1930s it was the use of sulfur dioxide was stopped. Then in 1877, Carl von Linde of Germany has built the first ammonia based system. This is a really a landmark in the history of refrigeration, because ammonia is one of the most important refrigerants, and even today there are large systems working with ammonia, and it's a very, very important refrigerant. And in 1885, Windhausen has built the first carbon dioxide based system in Germany. Carbon dioxide is also very important, and it was since it is non-toxic and non-flammable, it's a very safe refrigerant, and it was used mainly in marine refrigeration for almost 60 years. However, carbon dioxide has some problems. For example, it has very low critical temperature. That means if the external heat sink temperature is higher, condensation cannot take place. This is one of the main problems with carbon dioxide. In addition to that, the operating pressures are at least one order of magnitude higher than the rest of the refrigerants. As a result, carbon dioxide was stopped in again the 1930s or 1940s. But again, there is a renewed interest in carbon dioxide because of its many favorable properties. And in 1920, Copeland and Edwards have built isobutane based domestic refrigerators. Isobutane is a good refrigerant. It's a natural refrigerant, but one problem with isobutane is that it is highly flammable. So because of that reason, isobutane was stopped. However, again there is renewed interest in isobutane because of its other favorable properties. Now let us look at development of domestic refrigerators. As you know very well, domestic refrigerator is used for storing food products in houses, and everybody must have seen a domestic refrigerator. The early domestic refrigerator used to be called as an ice box. That means you have what you have here is you have a insulated box, and ice is stored at the top. So when ice is kept inside an insulated box, the air inside the box gets cooled as it comes in contact with ice. When it comes in contact with ice, air becomes heavy, so it drops down because of buoyancy. So as it goes down, the cold air cools the food product stored here, and it becomes warm, and it rises up again due to buoyancy. So a natural circulation current is set inside the ice box because of the presence of ice. So this is the simple principle of ice box, and it was very widely used for about 100 years without any change. But there are certain limitations with domestic ice box. For example, you cannot get very low temperatures, you cannot get sub-zero temperatures using ice. So this is one of the main problems. Another problem is the refrigeration stops once all the ice melts, so you have to continuously replenish ice. And the third problem is that you have to continuously drain the water that is formed because of the melting of ice. So these are the typical problems with the domestic ice box. As a result, people have tried to use artificial refrigeration methods in domestic refrigerators. So initial refrigerators use Vapour compression principle, and General Electric introduced the first mechanical domestic refrigerator in 1911 in USA, and this is followed by Frigidaire in 1915 and Kelvinator in 1918. Beginning with immediately after the First World War, there is a rapid growth in Vapour compression refrigeration systems. This is attributed to the following factors: the simultaneous development of electrical motors and compressors, because a typical compression system requires an efficient compressor and an electric motor to drive the compressor, and you need good shaft seals, and controls are required if you want to maintain the performance. And most important factor for the rapid growth is due to the introduction of CFCs in 1930s. We will see in subsequent lessons how CFCs have actually revolutionized the refrigeration technology. Okay, so beginning with 1920s or right after the First World War, there is a sudden rapid growth in Vapour compression refrigeration system and other types of refrigeration systems all over the world. Now let us look at development of air conditioning systems. There are several industries which require controlled conditions of temperature and humidity. For example, take the textile industry. The yarn used in textile is very sensitive to moisture content in the air, and it's also to some extent it's also sensitive to temperature. So if you want to maintain the output, you must maintain the temperature and humidity inside the textile mill at a required level. So this requires some kind of an air conditioning system which can keep the conditions at the required values. Also there are other industries like photographic industries which require again controlled temperature and humidity. So as a result, refrigerant systems were used in air conditioning system to maintain the required conditions. The first air conditioning system was installed by Eastman Kodak, the famous photographic film manufacturer, in 1891 in New York, to store photographic films. As you know, photographic films are very sensitive to moisture and temperature, so you require proper storage conditions. So this is the first example of air conditioning system. In fact, air conditioning systems were also introduced in movie theaters and in stock exchanges and all for providing human comfort, that is what is known as thermal comfort. Then the first domestic air conditioning system was installed in 1894 in Hamburg. Then in 1904, Willis Carrier has designed a central system using air washers, and in 1922, the same Willis Carrier has developed a centrifugal compressor for use in air conditioning systems. For his contribution to air conditioning industry and air conditioning science, Willis Carrier is known as father of air conditioning. Now let me show the basic principle of a vapor compression refrigerant system. Again, you have the four basic components here: evaporator, compressor, condenser, and an expansion valve. Let us begin at this point. Right after the expansion valve, a low pressure, low temperature liquid enters into the evaporator, where it boils by taking heat from the surroundings. So surroundings get cooled and you get a refrigeration effect in the surroundings. So as a result of this heat transfer, liquid becomes vapor, and this low pressure, low temperature vapor is compressed to high temperature and high pressure in this compressor. So the compressor compresses the vapor to high pressure, so that as it flows through the condenser, it can reject the heat of condensation to the surroundings, and again it can become a liquid at this point. So at this point still you have a high pressure liquid. So the high pressure liquid, again its pressure has to be brought down, so it flows through an expansion valve where it gets throttled and its pressure and temperature drops to the required level. So this is how the cycle continues, and as long as the compressor runs, you get a continuous refrigeration output. This could be the refrigerant system of a typical air conditioner. For example, in a room air conditioner, this portion is kept inside the room, whereas this portion is kept outside. So the room air gets cooled and the heat rejection takes place to the surrounding air, surrounding outside air. Okay. Now let us look at another type of refrigerant system, that is known as vapor absorption refrigerant system. You might have noticed that in vapor compression refrigerant systems, the energy input is in the form of mechanical energy to drive the compressor. And the principle of refrigeration is the evaporation of a volatile fluid. In vapor absorption systems also, refrigeration is obtained as a volatile fluid evaporates. However, the basic difference between a compression system and an absorption system lies in the fact the very fact that in a absorption system you don't use a mechanical compressor, you use what is known as a thermal compressor. So the main energy input to vapor absorption systems is in the form of heat, not mechanical energy. So let us look at the developments of these systems. In 1810, John Leslie has demonstrated the basic principle of vapor absorption using water and sulfuric acid. Now when you keep water in contact with sulfuric acid has a high affinity for water, so it can absorb the water vapor formed above the water. So as long as it has sufficient potential, it can continuously draw the water vapor from the water. Since this is an evaporation process, heat has to be supplied, so rest of the water gets cooled. That means using the principle of absorption and the high affinity of the absorbent, you produce a evaporation effect, and thereby you produce a refrigeration effect. This is the principle of vapor absorption refrigeration system. However, the process shown by Leslie is a discontinuous process. That means once the sulfuric acid becomes saturated, there won't be any more evaporation. So if you want to make it a practical system, you have to have again a continuous system. That means again you must have a cyclic process. So this is what is known as a vapor absorption refrigeration cycle. The first vapor absorption refrigeration cycle was suggested by Ferdinand Carr in 1860. He has used ammonia as the refrigerant and water as the absorbent. This is a very important invention, and aqua ammonia systems are very important, and they are also used even today. And in 1878, Windhausen has developed a continuous water sulfuric acid vapor absorption systems. In these systems, water is the refrigerant and sulfuric acid is the absorbent. However, sulfuric acid is corrosive, so later sulfuric acid is replaced by lithium bromide. So water lithium bromide systems have been developed. Again, water lithium bromide systems are very important because they are used today for providing air conditioning in large installations. And in 1922, two Swedish undergraduate students, Platen and Munters, have invented a very interesting vapor absorption system which does not require any mechanical device. That means it is a pumpless vapor absorption refrigeration system, and it requires only heat input for its operation. That is why this is called as a pumpless vapor absorption refrigeration system. And in 1926, Einstein has patented a pumpless vapor absorption system. This is also a pumpless system, but its principle is dramatically different from the one suggested by Platen and Munters. Now let me show the working principle of a vapor absorption refrigeration system. You can see that compared to the vapor compression system, the three components, condenser, expansion valve and evaporator, are common between these two systems. The only difference lies here. In a vapor compression system, we had a compressor here. The compressor was compressing the low pressure vapor to a high pressure. Whereas in vapor absorption system, instead of a mechanical compression, we have an arrangement which produces the same effect. Let us see how this is done. Here, instead of mechanical compressor, we have a component called absorber here, and a component called generator, and a solution pump. Let me explain the working principle here. Again, let us begin right after the expansion valve. After the expansion valve, we have low temperature, low pressure liquid, and this low temperature, low pressure liquid enters into the evaporator, where it takes heat from the surrounding water in this case and produces refrigeration effect in the surroundings. And during this process, the liquid becomes a vapor. Now what happens is, when this vapor comes in contact with the absorbent in this absorber, since the absorbent has high affinity for water, it absorbs the water vapor. That means this absorbent continuously draws the water vapor from the evaporator. So you have a continuous generation and continuous drawing of withdrawal of the water vapor from the evaporator. This is like the suction of a mechanical compressor. Then what happens is, as the absorbent absorbs water vapor, it becomes strong in refrigerant. So what we have to do is, we have to make it again weak. So how do we make it weak? Using a solution pump here, we compress this strong solution, that means strong in refrigerant, to high pressure using the solution pump, and then we pass it on to a component called generator. In the generator, what happens is, you supply high temperature heat to the solution strong in refrigerant. When you supply heat to the solution, refrigerant and absorbent get separated. When refrigerant and absorbent get separated, refrigerant vapor flows to the condenser, and since it is at a high pressure, it condenses in the condenser and forms a high pressure liquid which flows through the expansion valve, and the cycle is completed in this way. And the solution, which is now weaker in refrigerant, has to go back to the absorber, so it flows through a heat exchanger, and then its pressure has to be reduced. So we have an expansion valve here, where the pressure of the solution is reduced from the high pressure to the low pressure. So the low pressure solution, which is weak in refrigerant, goes back to the absorber. So the cycle is completed. That means a combination of absorber, solution pump and generator replaces the single component compressor in a vapor compression systems. And you can see that here the major input is in the form of heat. So these systems are very convenient, very advantageous, where you have abundant sources of waste heat. For example, you can use solar heat, or you can use waste heat available in industries for providing refrigeration. So absorption systems have their own advantages, and you can see that in this particular absorption system, a small amount of mechanical energy is required to run the pump. But compared to a compressor, the work required here is very small, because the work input is equal to integral VdP, where V is the specific volume and dP is the pressure difference. So since we are pumping a liquid here whose specific volume is very low, the required mechanical energy here is almost negligible compared to the heat energy. So this is the principle of vapor absorption refrigeration system. Now let us look at the plate and Munter system. As I was mentioning, a plate and Munter system is a pumpless system. That means you don't find any mechanical pump in this system, and the total pressure of the system is constant. That means at every point the total pressure remains constant. If the total pressure remains constant, how do you get refrigeration in the evaporator? So this is done by introducing a third gas, hydrogen. This third gas is inert. Okay, so when you introduce that into the system, it doesn't react with any of these other absorbent or refrigerant. So this third gas is confined to the low pressure part of the circuit. That means it is confined to evaporator and absorber. So because of the presence of hydrogen, what happens is that even though the total pressure remains constant, the partial pressure of the refrigerant reduces. That means you know that the total pressure is equal to partial pressure of the hydrogen plus partial pressure of ammonia plus partial pressure of water vapor. So if you introduce sufficient amount of hydrogen, you can see that the total pressure is constant, so the partial pressure of ammonia has to reduce. That means ammonia will be boiling at low pressure. Okay, so this is what produces the cooling effect in the evaporator. And here you can see that the major input is in the form of heat only, and here we use a component called bubble pump for pumping the solution from a low level to a high level. And these systems have many advantages. For example, since you don't have any mechanical component here, they are extremely reliable, and they are also silent in operation. That is the reason why these systems are typically used in small domestic refrigerators, in hotel rooms, etc., where you need a silent operation. So the use of these systems is mainly confined to these kind of applications. However, they are not used in large systems because their efficiency is typically very low. Now let us look at solar energy based refrigerant systems. Right from 1950s, people have been trying to use solar energy for providing refrigeration. Actually, this is a perfect match. If you can use solar energy for providing refrigeration, it's a good match, because the availability of solar energy matches with the demand for refrigeration. For example, on a hot day you require refrigeration. On a hot day, sun is available. So this is the motivation for developing solar energy based systems. So solar energy can be used in two ways. You can use it directly in the form of heat and have a vapor absorption refrigerant system. And you can also convert solar energy into electricity using, for example, photovoltaic cells, and use the electricity to run a motor and a compressor and use a vapor compression refrigerant system. That means solar energy based systems can be either compression systems or absorption systems. So as I was mentioning, the development began in 1950s, and it really picked up since 1965s. And the major reason behind this is that people have realized that our fossil fuel reserves are really limited, and refrigeration is a typically what is known as a low grade application. And it is said that for low grade applications you should not use high grade energy like electricity. Okay, it's like for example, you want to buy something in India and you have rupees and dollars in your pocket. Obviously it makes sense to spend rupees, not dollars. So it's similar analogy applies here. When you want refrigeration and when you have low grade energy is available, you should use low grade energy for providing refrigeration rather than wasting non-renewable fossil fuels. This is the main reason behind developing solar energy based systems, and as I said, it started in sometime in 1950s. Professor G.O.G. Lowe of America is one of the pioneers of solar based energy refrigeration systems. And the very first, I am just giving you a few examples. USSR has developed a 250 kg ice per day system using parabolic solar collectors. There are different types of solar collectors. You can have flat plate solar collector, parabolic solar collectors, and other concentrating type solar collectors. Depending upon the type of solar collectors that you use, you get different temperature outputs. So they have used parabolic solar concentrators, and they have built an absorption refrigerant system which could produce 250 kg of ice per day. And the first solar air conditioning system, that means solar energy was used to run a refrigerant system which was then used for providing air conditioning, was developed in Queensland, Australia in 1966. Now let us look at another common and important type of refrigerant system, that is known as gas cycle refrigerant system. This gas cycle refrigerant system is slightly different from the vapor refrigerant system. In vapor refrigerant system we call it as vapor cycle because in those cycles like vapor absorption and vapor compression systems, refrigeration is obtained as the working fluids undergoes a phase change. For example, in the evaporator, liquid becomes vapor, and in the condenser vapor becomes liquid. That means the cycle involves two phase change processes. So that is why we call them as vapor cycles. Whereas in the gas cycle, the cooling is obtained because of sensible cooling. So that means there is no phase change involved here. So this is the difference between a gas cycle system and a vapor cycle system. And the major principle behind gas cycle refrigerant system is that there are basically two principles. The most important principle is that when a high pressure gas expands in a turbine and produces external work, its temperature and pressure drops. So you can use the low temperature air or low temperature gas for providing refrigeration. That means you first compress the gas to a high pressure and then allow it to flow through a turbine where it can do external work, and in that process it can reduce its temperature and pressure, and this low temperature low pressure gas or air can then be used for producing refrigeration. This is the principle of gas cycle refrigeration. Let us look at some of the developments. The first gas cycle refrigerant system was developed by John Gorey in 1844. Actually, John Gorey is not a scientist, but he was a doctor. Not a scientist means he is not a mechanical engineer or a refrigeration engineer, but he was a doctor, and he, while treating his patients suffering from fever, he was in need of large quantities of ice, and he had difficulty in getting ice using any of the natural methods. I mean, the natural methods, as I said, are not reliable, so ice sometimes it was not available. So as a result of this, he has decided, or he wanted to build a system which is independent of your external circumstances and which guarantees a continuous provision of ice. Now, this led to the development of the first gas cycle refrigerant system. And even though he has proved the principle and he has built a system, we really do not know the commercial fate of these systems. Even though it is said that some of these systems were exported to other countries, they were not big commercial successes. After John Gorey, Alexander Kirk in 1862 has developed another gas cycle refrigerant system. This is a very important gas cycle refrigerant system, and this is very efficient also because this is based on what is known as a reverse Stirling cycle. We will see the cycles a little later. So this is based on reverse Stirling cycle, and it is quite efficient. And right now these systems are used in very low temperature cryogenic applications. And Bell and Coleman have carried out several improvements to the basic air cycle refrigerant system proposed by John Gorey. So sometimes air cycle refrigerant systems are also called as Bell and Coleman cycles. And Paul Gifford has perfected an open type of air cycle refrigerant system in 1875, and this open type systems are very widely used in aircraft air conditioning systems now. So let me show the working principle of an open type air cycle refrigerant systems. You have three major components here: a compressor, a heat exchanger, and an expander. So let me start at this point. Here you have an atmospheric pressure and low temperature air. Low temperature means the temperature is slightly lower than the surrounding temperature. So you have air whose temperature is slightly lower than the surrounding temperature and whose pressure is same as the atmospheric pressure. So this air is compressed in the compressor to high pressure. So at the exit of the compressor you have a high pressure air. So because the compression process, its temperature also increases, so it can reject heat in this heat exchanger to the cooling water that is flowing through the heat exchanger. So in the heat exchanger, the high pressure air rejects heat and its temperature drops. So at this point you have high pressure and warm air, not hot air but warm air. So this high pressure warm air then flows through an expander or turbine. So as it flows through the expander or turbine, it produces external work. Since energy is required for producing external work, it takes energy from itself. That means its temperature and pressure drop. So what you have here is a atmospheric pressure and low temperature air. So this low temperature air is sent to the cold room where it can provide refrigeration, cool the products and all, and in that process it picks up some heat and its temperature increases, and from here again it goes back to the compressor and this cycle is repeated. This is what is known as the open type air cycle refrigerant system, and as I mentioned, this is mainly used for providing air conditioning in aircrafts. This system is not very efficient and it is also bulky, but why we use this in aircraft is that the components required for this system, typically the compressor and turbine, which are the main bulky components, are already there on the aircraft. So an aircraft engine requires a compressor and a turbine. So instead of adding a fresh compressor and turbine for the air conditioning system, you can use the existing compressor and turbine. So this is the reason why this system is mainly used in aircraft air conditioning systems. And you can also have a closed cycle refrigerant system using gases. In principle, anything other than air, you can also use other gases. For example, you can use helium, okay, or any other gas. Now let me discuss another important and commonly used refrigerant system, what is known as vapor jet refrigerant system. This here also it's also a vapor cycle. That means here also you produce refrigeration by evaporation. But again, the major difference between this and compression system lies in the way in which you maintain the pressure in the evaporator and the way in which you compress the evaporated vapor. So that's where the major difference lies. The basic principle I'll explain here. Whenever you have okay, I will show the schematic a little later, but let me just explain the history here. The first vapor jet refrigerant system was designed and developed by French engineer Maurice Leblanc in 1907. So he has used steam. Then in Westinghouse has commercialized these systems in 1909 in Paris. And from 1910 onwards, these systems have been used very widely in warships, breweries, etc. And the Russian engineer Badel has developed closed cycle vapor jet systems in 1955. So he did not use steam, but he used other refrigerants for providing the refrigeration. Let me explain the working principle of this. This is a typical steam jet refrigeration system. What we have here is an evaporator drum and a condenser drum. So this is a condenser drum and this is an evaporator drum. This evaporator drum consists of water and this condenser drum also consists of water, and the motive force or the prime energy input to this system is in the form of motive steam. Motive steam means high pressure steam. So when this high pressure steam flows through this nozzle, its pressure reduces and it gains kinetic energy. That means at the exit of the nozzle you have a fast moving motive steam. So because of its high velocity, it can entrain the vapor from this drum. That means whatever vapor is there in this drum gets entrained by this fast moving motive steam, right. So vapor is removed from this drum. So once the vapor is removed, more vapor is formed by evaporation of the remaining water. That means the water evaporates to provide the continuous vapor. So as a result, rest of the water gets cooled because evaporation is endothermic. So you have production of cold water here. Okay. Now what happens to this vapor? This motive steam plus the vapor that is evaporating in the evaporator both get mixed and then they flow through a diffuser. In the diffuser, what happens is you convert the kinetic energy back to pressure. That means at the end of the diffuser you again have a high pressure steam. Okay, this high pressure steam now comes in contact with the cooling water that is flowing through this heat exchanger. When it comes in contact with the cooling water flowing through the steam, it rejects the latent heat of condensation and it condenses. So ultimately you have condensed water here. That means you evaporate the liquid water in this evaporated drum using the motive steam, and then condense the motive steam and the evaporated vapor using a diffuser, increase its pressure in the diffuser, then using cooling water you take the heat out of the vapor and condense it. Then to complete the cycle, what we have to do is we have to again split this liquid into two parts, and you have to send the makeup water back to the evaporated drum, and the rest of the water again has to go back to the boiler feed pump to complete the circuit. This is the principle of a steam jet refrigeration system. And we use here, as you can see, we do not use any mechanical compressor here. The mechanical compressor is replaced by a combination of a nozzle, ejector, diffuser and all. So this is sometimes known as an ejector refrigeration system, and the principle of ejector was actually used in the beginning to pump out air leaked into the condensers of power plants. So this is the first application of ejectors. Later the same principle was extended to the refrigeration systems. In principle, you can use any other working fluid other than steam. You can also have closed cycle systems using refrigerants. Okay, you need not use. If you use refrigerants, you can produce lower temperatures. So when you are using water, you can't get temperatures lower than 0 degrees centigrade. That is one limitation of water. Okay, these systems were used in the beginning in several, as I said, in warships and breweries and all. And this is also used for providing what is known as vacuum cooling in food products. That means in the evaporated drum, what you have seen earlier, you can put the food products itself and take out the moisture from the food products using an ejector. So when you are taking out moisture from the food products using an ejector, the food products get cooled. Okay, so this is the principle behind vacuum cooling, right? So this is the steam jet refrigerant system. Now let us look at thermoelectric refrigerant system. So Seebeck effect. Seebeck effect is reported in Germany, and I am sure most of you are familiar with Seebeck effect. Anyway, let me just recapitulate this. What we have here is in a Seebeck effect, you have two dissimilar metals, and when you maintain these two junctions, you have let us say that a metal A and a metal B, and these are the two junctions. And let us say that you are maintaining these two junctions at two different temperatures. Let me say that you have this junction is a hot junction and this junction is a cold junction. So once you have two dissimilar metals joined together, and when you are maintaining the junctions at two different temperatures, an EMF will be developed in the circuit. That means you will see that a current is flowing through the circuit. This is what is known as Seebeck effect, and this is reported in Germany in 1821. Next, Peltier has found an effect which is the reverse of Seebeck effect. Okay, this happened in 1834. So let me explain what is the Peltier's effect. You have seen the Seebeck effect, and let us look at the reverse Peltier effect. That means you have, let us say that again two different materials A and B. Okay, and now let us say that you are passing electrical current through this. Okay, you connect it to a battery and allow current to flow through this. When current flows through this, that means when electrons flow through this, you find that one junction becomes cold and the other junction becomes hot. That means by joining two dissimilar metals and by allowing current to flow through this, you can produce refrigeration at one end and you can reject heat at the other end. So this becomes, let us say, hot end, and this becomes your cold end. So you get refrigeration effect at this point. So this is the principle behind Peltier effect. So using the Peltier effect, Lenz has actually demonstrated the Peltier effect by freezing a drop of water in 1838, and he has used bismuth and antimony as the materials. But later it was found that metals are not really the ideal materials for use in thermoelectric refrigerant systems. because of as you know very well, metals have very high electrical conductivity, which is required in a thermoelectric system, but they also have high thermal conductivity. Because the high thermal conductivity, it is difficult to maintain the cold and hot junctions at the particular temperatures, because heat will always flow from hot junction to cold junction, and since the thermal conductivity is high, the temperature gradient tends to reduce. So this is the problem with metals. That means metals typically have low, what is known as a low thermoelectric powers. So if you want to develop a good thermoelectric system, you have to have a material having high electrical conductivity but low thermal conductivity. For almost 100 years, people could not find any suitable materials. However, in 1940s, people have invented semiconductor materials, and semiconductor materials have reasonably high electrical conductivity and low thermal conductivity. That means they have high thermoelectric power. So now you can, the systems are ready, you can make thermoelectric systems using semiconductor materials. Semiconductor materials typically, you know, that have P type and N type. You can have two types of semiconductor materials, P and N type. So a typical semiconductor thermoelectric element consists of a P type element and an N type element joined together. So you have two junctions joining the P and N type elements, and when you give a power supply, a DC power supply at low voltage, electrons will flow, and when the electrons jump from P to N, they absorb energy, and when they jump from N to P, they reject energy. That means you get a cold junction on one side and a hot junction on the other side. Okay, this is the principle of semiconductor based thermoelectric reference system. However, you cannot use just one P element and one element, because the cooling that you get with just one element is too low of any to be of any practical use. So in practice, what is done is you stack a large number of thermoelectric elements in series, and you make a thermoelectric module so that you can produce a sizable amount of refrigeration. Okay, so this is the principle of modern day semiconductor based thermoelectric devices. And later, actually, the Russian scientist Iov is one of the major pioneers in the area of semiconductor based thermoelectric systems, and Russia has developed several domestic refrigerators using this principle. And in USA in 1960s, they have developed large air conditioning systems using the thermoelectric principle. One major problem with thermoelectric principle is that the efficiencies are typically low compared to vapor compression systems. However, they have the advantage that they are silent in operation, and they are very reliable, because you are not really using any mechanical component there, and you can use the same thermoelectric module by changing the direction of current electron flow, either for heating application or for cooling application. This is one of the advantages of thermoelectric systems. So let me show the working principle of a thermoelectric module. As I was mentioning, it consists of a P element and a N element. So this makes one thermoelectric element. So several such elements are stacked in series, and this forms a thermoelectric module. And all the cold junctions are collected on one side. So this is the cold junction, and all the hot junctions are connected on the other side. Now when you connect this thermoelectric module to a DC source, let us say at 12 volts, and when you start giving the power supply, electron will flow through the P and N elements and through the thermoelectric module. And as I mentioned, as electrons flow from P to N, they produce a cooling effect. So you have cooling on this side. Okay, and when it flows from N to P, you get a heating effect. So you can see that this junction is hot. So by designing them in this manner and by stacking them together, you get cooling on one side and heating on the other side. Okay, and of course we have to have some electrical insulators to avoid shorting and all that. And as I was telling, depending upon your requirement, if you reverse the current flow, you can use the same side for you can have either cooling on this side or heating on this side, just by reversing the direction of the flow. So this is the principle of your thermoelectric reference system based on semiconductors. Right now these systems are used in small portable as small portable refrigerators. For example, you can carry it along with you. Okay, and this is also used for carrying vaccines and all to remote areas. These are the main applications of thermoelectric systems at the present moment, and they are also used in certain high efficiency computers for cooling the computer chips. Now let us look at another interesting system called Vortex tube system. Let me again explain the working principle of this. This is a very simple system. What you have is a tube, a long tube with a valve on one side and a central hole on the other side, and let us say that using a nozzle, this is a nozzle, and through this nozzle you allow high pressure air, So when you allow high pressure air through to enter into this tube through this nozzle, at the end of the nozzle, at this point the pressure is converted into kinetic energy. That means its velocity increases tremendously, and when this high velocity air enters into this tube, it undergoes a swirling motion. So you get a swirling motion. So air undergoes a swirling motion, and during this motion and during its passage from one end to other, a cold core is developed near the axis. That means you have a cold air stream at the axis and hot air stream around the cold air stream. So you have near the periphery you have hot air, and in the central portion you have cold air. So the hot air escapes in this through this, and the cold air comes out through the opening on the other side. So this is known as a counterflow type of vortex tube. So you can see that what you need here is a simple tube and a supply of high pressure air. All that is required is that, okay. And depending upon the valve position, you can get different temperatures of cold air and different amounts of cold air. So this is the principle of vortex tube refrigeration systems. Vortex tube refrigeration systems are not very efficient, but they have certain advantages. So for example, it's very simple, and all that you need is a compressed air supply. Okay, so that's why these systems are mainly used for cooling machine elements and all. For example, in machine tools, you want some localized cooling, you can use a vortex tube, and you supply compressed air to the vortex tube and get the refrigeration effect. And this is also used in jackets worn by the miners. When the miners go into deep mines, they require cooling because it's very hot in the mines. So they can carry the vortex tube in their jackets, and the vortex tube is typically connected to high pressure air supply, and they get cooling because the jacket supplies cold air to different parts of the body, and the different parts of the body get cooled. In addition to this, you can also supply the fresh air continuously to the miners. So this is the advantage, and this is the reason why vortex tube systems are used in mines. And as I was mentioning, in 1931, George Rank has discovered the vortex tube effect. And in 1945, actual principle behind vortex tube is very complicated. I mean, the analysis is also very complicated, and for many years, even the people have demonstrated the effect, they could not really explain the physics behind the vortex tube operation. And in 1945, German physicist Rudolf Hilsch has given a scientific explanation for vortex tube effect. That's why the vortex tube is sometimes known as Rank and Hilsch tube. And since then, as I was mentioning, this is mainly used for spot cooling in machine elements, in electrical components, and also in mines for cooling the miners. Now let me conclude this lesson. We have in this lesson we have defined refrigeration and air conditioning, and we have outlined the historical aspects of various natural and artificial refrigeration methods. And while doing so, we have also explained the working principle of these systems in brief. And when we discuss these systems, we will explain the working principle once again in detail. Okay, and right now the main focus is to develop refrigeration systems. The modern life, you cannot imagine modern life without refrigeration and air conditioning. It has become an essential part of our life. So almost all the industries require refrigeration or air conditioning, and we need air conditioning for thermal comfort. So air conditioning systems are very widespread, and it is almost a common item in all households in the form of a domestic refrigerator. So what are the issues right now with refrigeration and air conditioning? The main issues are developing systems that are energy efficient, because typically in a refrigeration system or air conditioning system requires energy input. So you have to make systems which are efficient, energy efficient, and there are also certain environmental issues related to refrigerant systems. So whatever systems you develop should be environment friendly, and they should be affordable. If you want to make it available to everybody, you have to make them affordable. So these are the main issues, current issues in refrigeration development, and the studies are going on these aspects, and we will discuss these aspects in detail in subsequent lessons. Thank you.